Hi there, Level 2 Physics. So we're continuing on with forces, and we'll look at motion and equilibrium a little bit later. But first up to say that your textbook, Housden, contains this information in Chapter 10. So Sir Isaac Newton was an English physicist and mathematician that lived in the late 1600s, early 1700s, and he discovered a few relationships between forces and their effects on different objects. First one, well, he published them in a book, and the first one you might have heard of before. It's his first law. They're 1, 2, and 3. And the first one says that every body continues to go in a state of rest or uniform motion in a straight line unless a resultant or a net force acts upon it. So that basically means that something that is stationary will remain stationary, and something that is moving in a straight line at a constant speed will continue to do so unless there is an unbalanced or a resultant or a net force acting upon that object or body. So for example, Father Christmas, poor guy, what happened here? So there was a resultant force acting on him, the wall on the motorbike, and so he continued to move beyond the wall stopping the motorbike. So he continues at a constant velocity until an external resultant force acts upon him. So Newton's first law also then introduced the idea of inertia. Inertia basically means that an object will remain at rest or continue to move in a constant velocity, and that means same speed, same direction. And we can think of a measure of inertia as mass. So in class I'll show you the coin dropping into the cup. So we flick the piece of cardboard away and the coin falls into the cup because the coin is at a state of rest. So the practical measure of inertia is mass. So the heavier an object is, the greater the mass of the body, in other words, the greater its inertia. So the likelihood of the girl pushing the elephant is not great, but the elephant may push the girl quite easily. Practical application of this is a seat belt in a car. Now on the right hand side here you can see this blue T-shaped pendulum, and when the car suddenly brakes, that pendulum will move forward, which will push this bar over here, the pink one, because it's called a locking rod and it's on a pivot. So when the ratchet wheel is caused to jam, then the wheel will stop spinning and the seatbelt will not be able to be pulled out further, and so it grabs the person sitting in the seat and prevents them from hitting the dashboard. So when forces are balanced, Newton's first law, then the objects stay at rest, and when the object is already in motion, it will remain in motion as long as it has the same speed and direction. We also call this a state of equilibrium. So if the forces are balanced, so 8 newtons to the right and to the left, then we have a state of equilibrium. And here we have 3 forces acting on the same object, and they are equilibrium. Have a look in your text on page 114. There are 3 more examples on the top left of the page for you to have a look at. And then finally, for Newton's first law, we'll have to use these 2 conditions of a body for equilibrium, and these are that the sum of the forces in any direction will be 0, and we will look a little bit later at torques, but for now just make a note that the sum of the torques about any point is 0. Highlight this information in your book because you will need to learn it. And so hopefully you've been asking yourself the question, well, what then happens when forces are not balanced? So for example, a massive truck on the left will force the car on the right to move. And that's when we have a resultant force, or an unbalanced force, or a net force that is not zero. And what that force then does is it changes the body's velocity. In other words, it accelerates the body. Remember F equals ma? Well, here we go. It's Newton's second law. So the rate of change of momentum of the body is directly proportional to the resultant forces acting upon it, and it will take place in the direction of that force. It can also be said that the direction of the object's acceleration is the same as the direction of the resultant force of the object. So the resultant force produces a change in the body's momentum, which produces an acceleration. So if the body is at rest, it will move if there's a resultant force, and if it's already in motion, it will either accelerate or decelerate depending on the direction of the resultant force. So we've come across F equals ma before, and we define it because we state that 1 Newton is the force that causes a mass of 1 kilogram to accelerate at a rate of 1 meter per second squared. We already know that force is measured in newtons, capital N. Mass is measured in kilograms, small letter kg, and acceleration is measured in meters per second squared, which is m.s to the minus 2. This slide is only in here for the mathematical minded, so don't worry about it too much, but basically force is proportional to the change in momentum over change in time, so that's mv over delta t. So if you look at the initial velocity and the final velocity, final minus initial for delta t, then we end up getting an equation that looks like this. We take out m as the common variable, and we also know acceleration is v minus u over t, and so you can substitute that in for that part of the equation, and you end up with force is proportional to mass times acceleration. And it's worthwhile remembering that this proportion sign can be replaced with an equal sign and a k value, or a constant. And in this instance, our k value is always 1. And so we rewrite it as F equals ma. So from F equals ma, we can determine that acceleration is directly proportional to the force applied. So the bigger the force applied, the greater the acceleration will be. Right? It's a straight line graph through the origin. And if we plotted acceleration versus the inverse of mass, or against the inverse of mass, we'll get a curve relationship. Right? So A is proportional to 1 over m, an inverse relationship. We'll look more at graphs when we do the next internal. And so we can now plot A is proportional to 1 over m. So you can see here A plotted against 1 over m, and that again will give me a straight line through the origin. So to summarize, Newton's second law is may be used in two forms: F equals ma, as well as F equals the change in momentum over the change in time, where F is called the resultant force, or the net force, or the unbalanced force.